Welcome to this video in the nuclear chemistry unit. This is 18.3, where we are going to continue the inside story. Today you guys are going to be learning all about ionizing radiation and its dangers, Geiger counters and how they detect radioactivity, and how exactly we determine the types of radioactive emissions different substances will spit out, and we are going to do that via magnetic fields. If you haven't already done so, make sure that you have downloaded and printed your companion worksheet and you have a pencil or a pen to take notes with, because we are about to get started. Let's go. The first part of today's video is going to be all about introducing you to ionizing radiation. And just based on its name, I bet you can figure a little bit about what that type of radiation will actually do to atoms. In order to introduce the topic, I'm going to show you guys a short video that I pulled off of YouTube. Make sure you take notes on it and cover all the important things that the video has to offer. After the video, I'll be back.
Ionizing radiation, which is energy that's given off by radioactive materials. Ionizing radiation has a lot of energy, much more than the low energy radiation from radio waves, cell phones, and microwaves. These types of low energy radiation are called non-ionizing radiation. Ionizing radiation has potential for interacting with and changing atoms and molecules. This is an important distinction which many people may not realize. For simplicity, we'll just refer to it as radiation. If radiation hits the cells in the body, it can damage or even kill the cells. The amount of energy that the body absorbs from this radiation is called the radiation dose. At high doses, and when most of the body is exposed, enough cells die to impair the function of various organs in the body, and that can lead to really serious health effects, including death. If only a specific part of the body is exposed and the dose is high enough, it could lead to localized effects, such as skin injury. At low doses, if any cells are damaged, the cells may repair that damage with no consequence, or the cells may leave the damage unrepaired or repair it incorrectly. And these may have long-term consequences and could potentially increase the risk of cancer.
You used the word exposed. Is this term used differently for radiation hazards than other environmental hazards?
It is. When our bodies absorb the energy from radiation, we're being exposed to radiation. We don't have to come in contact necessarily with any radioactive materials. If we walk away from the source of radiation, the exposure stops.
So like with an X-ray, you're exposed while the X-ray is being taken, but you don't take any of the radiation home with you.
Exactly.
So just to recap the video, ionizing radiation, or IR, is any radiation with enough velocity or energy to remove an electron from an atom when it hits it. And essentially, if you have enough exposure to ionizing radiation, that will break down atoms, which is no good in the grand scheme of things. Now, examples of common IR would be your alpha particles, your beta, and of course your most energetic particle that's on there, your gamma radiation. But there's also some non-table O emissions. High energy UV light outside does damage to skin cells and is also used in the food industry. And of course there are X-rays. By the way, there is a maximum number of X-rays that you can have in a year. So if you have really bad dental problems, you might have to actually space that out. Why the ionizing radiation is actually bad for you comes really down to a genetic level. And essentially, if it enters your cells, all your cells have nuclei in them, and the nuclei, contain the instructions to code for whatever it is that cell is actually going to do. If the ionizing radiation gets in there and actually hits a nucleotide, knocks it out, you could have a frame shift, you could have an insertion, you could have something where you don't want it, and that could result in a mutation, which we have seen in many places where there was nuclear testing, or sadly in Japan where the 2 atomic bombs were dropped in World War II. Here are some of the issues and maladies that can happen from exposure to ionizing radiation. Some in the short term, some in the long term. Now listen, not all ionizing radiation is bad. A lot of it is used in the food industry, where exposing different foods to ionizing radiation will improve the safety and extend the shelf life. You got to figure, if it's bad for our cells, microorganisms, it's got to be really bad for us. So what they will do is hit food with small doses of ionizing radiation to kill all the microorganisms, and therefore your food doesn't spoil as fast, and there's no creepy crawlies when you go shuck your corn or any of that. It has helped food service, especially when you are transporting food over many, many, many miles. It keeps it intact to be sold. Now, you're probably sitting there going, is the food now radioactive since it's been irradiated? And you have nothing to worry about. The energy that is actually used in food irradiations is not enough to cause the food to become radioactive. So go ahead and eat your apple. Part 2 of this video is all about the way we detect radiation, which is using an instrument called a Geiger counter. So I'm going to play a quick video for you guys and want you to check it out and make sure you take notes on the content of the video and understand how a Geiger counter works.
A Geiger counter is an instrument that measures ionizing radiation. Jay Sheldon explains how it works.
A Geiger counter has inside of it a Geiger tube, and a Geiger counter only detects ionizing radiation. That ionizing radiation knocks electrons off of atoms and molecules that it happens to encounter. So the detector has to be sensitive to that. So inside every Geiger counter there is one or more Geiger tubes. The tube has a wire going down the middle and a metal can around the outside and kind of a special mixture of gases. So ionizing radiation comes along, it has to get through the metal and it will ionize some of the gas. There is a huge voltage difference between the wire and the can, which means that if there's any charge in the air, it'll get very strongly. The electrons get pulled down to the wire and the positive ions get pushed out to the can. It's a very, very strong electric field. So if you create a bunch of free electrons, which is what ionizing radiation does, it knocks them out, the electron gets pulled very strongly towards the central wire. Now, of course, that ionizing radiation may ionize a few atoms, but here's the real key. You get amplification and you get a cascade. You get one electron, which is now loose from its atom, can start moving very fast towards the wire, so fast that it itself becomes ionizing radiation. And when it bumps into another air molecule, it will knock an electron or two off of it. Now you have two, and they now get accelerated and they bump into another, and you get more and more. You get a cascade of electrons being created by this process. That pulse of electrons hitting the wire, that makes a tick, makes a light blink, makes a counter go up by 1. So it directly is detecting ions created by ionizing radiation, which of course is what we need.
Okay, so summing up that last video, a Geiger counter is indeed a device that is used to detect radioactivity. And as you saw in the video, each click means that a particle is found. Now, one of the limitations to the Geiger counter is that it will never tell you the type of emission you have, just that an emission has occurred. So for us, we have to understand how the internal structure of the Geiger counter can detect radiation. So to do that, I'm going to click on an animation. Be right back. Okay, here we are looking at a Geiger counter and specifically the Mueller tube or the Geiger tube, which is the most important part because it does all the detecting. So here I have some uranium ore that happens to be radioactive. You can see it is emitting particles as we speak. So how does this tube and the corresponding Geiger counter detect radiation? Well, essentially what winds up happening is as radiation is emitted, whether it's an alpha, beta, gamma, whatever, high speed, it's going to pass through the Mueller tube. And inside here is an inert gas. In this case, it is argon. Well, every time one of those particles hits a argon gas particle, it knocks off an electron. That electron, therefore, then is attracted to the positive wire that is inside here, and every time one of those hits that positive wire, an electric pulse is created, and it registers on the Geiger counter. That electric pulse is translated into a sound, and what you really get is a click. Each click indicates that a single atom has decayed and one emission has been detected, and so more clicking means more radiation, which is never good. A normal level of radiation, which we call background radiation, gets you about 50 clicks per minute. To contrast that, if you were to go to the site of a nuclear disaster, maybe a nuclear bomb test site, you might actually get, instead of 50 clicks per minute, you may get 50 clicks per second. So it's pretty significant. A lot of people out there just buy their own Geiger counters just to test radiation because, you never know. Part 3 and the final part of our video talks about how magnetic fields are used to differentiate the different types of radioactive emissions. So in order to do that, I'm going to throw back a name at you. It's Ernie Rutherford. And you will remember Ernie Rutherford from when we used to talk in the fall about the atom. It was very early on in our chemistry careers. That's right, you remember that Ernie Rutherford was responsible for the gold foil experiment where he shot, that's right, alpha particles at a thin sheet of gold foil, and if you recall his findings, most of the particles went through that foil and went through undeflected. Some of them were repelled away, and occasionally some of them, when they scored a direct hit on something that was in the atom, they didn't quite know what that was yet, wound up rebounding back towards the source. At the end of the day, it was this experiment and the fact that the alpha particles were not only deflected by the nucleus but repelled that led us towards the idea that our nucleus did indeed have a solid core and was positively charged. So you might be sitting there saying, well, why in God's name is he rehashing the gold foil experiment? And it's really the idea of the repulsion of the alpha particles to the nucleus that's going to bring me to my next point. How we determine emission type is completely based on attractions, repulsions, and magnetic fields. I'm going to show you a quick video. I want you to check this out, and then I'll be back to sum it up.
Radioactive elements can spontaneously emit 3 different types of radiation: alpha particles, beta particles, and gamma rays. Carbon-14 spontaneously emits beta particles from its nuclei. Since beta particles are attracted to the positive plate of an applied electric field, they must be negatively charged. In fact, beta particles are electrons that are formed and then emitted from the nuclei of certain radioactive isotopes. In the decay process, a neutron is converted to a proton and a beta particle. Cobalt-60 is used for radiation therapy and treating certain cancers. It spontaneously emits gamma rays from its nuclei. Since gamma rays are undeflected by an applied electrical field, they have no electrical charge. Gamma rays are very high-energy electromagnetic radiation. They have no detectable charge or mass. Radon-222 is being formed continuously in our environment by decay of uranium-238. Radon, being a noble gas, is chemically unreactive. Therefore, it is not trapped by chemical processes in the soil or water and is free to seep up from the ground and into homes. Radon spontaneously emits alpha particles from its nuclei. Since alpha particles are attracted to the negative plate of an applied electrical field, they must be positively charged. In fact, an alpha particle is composed of 2 protons and 2 neutrons. It is equivalent to a helium-4 nucleus. Both alpha and beta particles are deflected by an applied electrical field, while gamma rays are unaffected. Also note that alpha particles are deflected less by the applied electrical field compared to beta particles due to their higher mass. An alpha particle, composed of 2 protons and 2 neutrons, is approximately 7,000 times the mass of a beta particle.
So that video is an oldie but a goodie, but it really does a nice job explaining the effects of a magnetic field on the radioactive emissions. Just to summarize what it said, here we can see we have these red circle particles that look like they are being attracted towards the negative plate, which is here. What that must mean, because it was attracted to the negative plate, is that whatever this particle is here, it must be a positively charged particle. And that was our alpha particle. Down here, we have a particle that is a green circle that's being attracted to the positive plate. That means that that must have a negative charge, and we know that that is our beta particle. One of the things the video did make note of is the fact that the alpha particle was deflected less than the beta particle, because the mass of an alpha particle is 4 atomic mass units versus the beta particle, which is a high-speed electron and has virtually no mass, so it actually got deflected more. The one thing that we didn't really see affected by either the positive or the negative plate was this yellow line that's here, and that is your gamma radiation, which you guys know has no mass and no charge. So remember, it's magnetic fields that are used to differentiate the different types of emissions based on how they fare versus the positive and negative plates. So that's it for me. Hope you had a good time furthering your knowledge about radiation. If there was anything that you guys were struggling with, make sure you bring it to the burning questions segment tomorrow in class. Gotta say adios. I'll see you all on the flip side. Peace out.
That's all, folks.